ahead and start now. So today we're starting our next section of the class, chapters 9 through 11. Chapter 9 is entitled Alcohols, Ethers, and Related Compounds. Today we'll talk about three of those types of compounds: alcohols, ethers, and epoxides. This is a lengthy chapter. We've got 4 days on the schedule for it, and it'll probably end up being more like 4.5 days because there's a lot of chemistry in this section. Today we'll just go over introductory material largely. We will introduce the structures we're talking about and some vocabulary associated with them. We'll spend some time talking about our favorite subject of nomenclature. And then we'll talk about some interesting alcohols. The figure on the model on the screen here is of an interesting ether. This is a polyether. This molecule is called brevetoxin B. It's a very large molecule, as you can see from this model here. And it's known as a ladder polyether because it has a bunch of cyclic ethers fused together. So the red balls are indicative of the ethers. And so the polycyclic ring system kind of makes a ladder-like structure. This molecule is long enough that it can insert itself into cell membranes similar to amphotericin B and allow ions to flow in and out. That's part of how it functions as a toxin, hence the name brevetoxin B. And the reason it's on this page with a picture of a red tide is that brevetoxin B is produced by the algae that cause red tides. Okay, so these algae, they grow, they bloom in certain areas. They cause this red color to appear in the ocean or wherever they're blooming, and then they kill lots of the marine life in that area. And brevetoxin is thought to be possible for or responsible for some of that death. If you eat shellfish that came from an area where there was a red tide, you can get sick. Probably not have enough of it to die. Interestingly enough, there are some people who have speculated that when Moses turned the waters red in the Old Testament, that was actually a red tide event because there was a lot of death of the fish and so forth from that water. So I don't, nobody knows, no way to prove or not, but it's fun to think about. But the point is, this molecule is an interesting ether that comes from nature, and there are many, many different interesting ethers and alcohols and epoxides that we're going to talk about. So the structures, general structures of these compounds we're learning about in this chapter are shown right here on the board. And you can see that an epoxide is actually a type of ether. So you might wonder, why do we consider it separately? It is due to the fact that the oxygen is part of a highly strained three-membered ring. So when you have that ether as part of a strained three-membered ring, it will have additional reactivity that a normal ether will not. And so that's why we'll talk about epoxides separately, because they'll have their own set of reactions they will undergo that normal ethers will not. There's some vocabulary associated with these compounds that we need to learn. So for the alcohols, we have here a classification system that is identical to the classification system that we used for alkyl halides, primary, secondary, and tertiary, depending on the number of alkyl groups attached to the carbon that bears the oxygen. So that classification system should be familiar to you. And in a normal alcohol, these are all alkyl groups. We can have alcohols attached to sp2 carbons. This particular type of alcohol would be referred to as an enol. And then if we have the OH group attached to a benzene ring or an aromatic ring, that is referred to as a phenol. So phenyl is a way of referring to a benzene ring as a substituent. So we would call this a phenol. So we're not going to learn about enols and phenols in this chapter because much like vinyl halides and aryl halides, they have different reactivity than normal alcohols. So we'll learn about enols and phenols in 352M. Okay, we'll cover their chemistry next semester. But we do want to know the structures and what they're called at this point. So with ethers, we have classifications of ethers based on whether the two alkyl groups attached to the oxygen are the same or different. So this is diethyl ether, and we'll learn the naming system in a minute, but we would refer to it as a symmetrical ether. This is a fun one to draw at this time of the year because it looks like a bat, so it's a nice Halloween type molecule. But we can also have ethers with two different alkyl groups. This one is an unsymmetrical ether. Okay, so these are just some categories that we have for referring to alcohols and ethers. Here we have a figure showing us electrostatic potential maps of an alcohol, an ether, and an epoxide. And we see they have something in common with alkyl halides. The oxygen is more electronegative than carbon. So we have bonds, 1 or 2 carbon-oxygen bonds, depending on whether it's an alcohol or an ether, polarized towards the oxygen. So we end up with electrophilic carbons. And we had the same situation with alkyl halides. So that would suggest that alcohols and ethers can undergo the same types of reactions that alkyl halides could, namely substitutions or eliminations. The problem is that alcohols and ethers are terrible leaving groups. Hydroxide is very basic. If you were to make a leaving group out of half of our ether, that would be methoxide. That's also very, very basic. So the high basicity of hydroxide or alkoxides prevents alcohols and ethers from undergoing the same reactions that alkyl halides do unless you convert them into a good leaving group first. So what we'll see in this chapter is that before you can have substitutions or eliminations with these compounds, you have to convert the alcohol or the ether into a good leaving group, and we'll discuss how that is done. The epoxides are different, though, because of that strain in the ring. If we perform a substitution reaction that breaks one of our carbon-oxygen bonds and releases a highly basic leaving group, even though that wouldn't be favored ordinarily, the release of the ring strain is thermodynamically favored. And so you'll actually see epoxides undergoing some substitutions that alcohols and ethers will not. Any questions about the structures of alcohols, ethers, and epoxides? All right, let's talk about the nomenclature then. So we'll start with alcohols. And the nomenclature of alcohols is unique compared to other compounds that we have talked about so far. So we have a new suffix. The suffix is ol. OL, that goes at the end of every alcohol. Okay? And then something else that's new about alcohol nomenclature is that the OH group has priority in the nomenclature system over other functional groups. So what this does is it changes how we name and how we number the chains of alcohols, okay? The fact that they have this priority. So the 3 steps we're going to follow when we are naming alcohols, we're going to find, first of all, find the longest chain that contains the OH group. So what that means is that the carbon that the OH is attached to has to be part of the chain. It can't be part of a substituent. So it might not be the longest overall chain in the molecule. Okay? So once we've done that, we need to number the chain to give the lowest number to the OH group. So the carbon that the OH group is coming off of needs to have the lowest number. So this is different from the first point of difference rule that we used previously for numbering the chains of alkanes or alkyl halides. And once we've done these two things, then everything else is going to be the same. We're going to follow other nomenclature rules, basically meaning that when we have substituents other than the OH group, we would name and number and order those substituents in the same way as we learned previously. So let's look at a couple of examples. That's the best way to learn this system. So let's draw an example on the board here. And let's see if we have enough. Need a couple more carbons. All right. So what is our longest chain of carbons that includes the carbon bearing the OH? Seven, yes. Okay. What's the longest chain in the molecule? Right. So we don't use the longest chain this time. The longest chain is here, but the longest chain containing the OH group goes this way. So since it's 7, what's the parent name of our compound going to be? Heptane. And then we drop the E and add our suffix. We're going to end up with heptanol. Okay. So now we need a number associated with the OH group, and we're going to put that number in front of the parent. So what number is going to go in front of heptanol? 1, exactly. Okay. So we're going to number. It's a primary alcohol. It's at the end of the chain, so we're going to number like this. Now, if you look in the book, it shows the 1 going in after the parent name and before the suffix. It's heptan-1-all. So apparently, the members of IUPAC who come up with nomenclature had too much time on their hands and didn't have anything better to do, and they decided they needed to change the way that we named alcohols. Instead of putting the number in front of the parent, they decided that it was better to put it in the middle, which I think is silly, because it's a lot easier to say 1-heptanol than to say heptan-1-all. Okay, so we're going to do it the old way. They just switched it in the new edition of the book. It was a recent change, but I trust that if you see the 1 before the suffix, that's not going to trip you up. That you'll be able to figure out that both names mean the same thing. But we're going to go ahead and do it this way. So now we're on to number 3, following other nomenclature rules. How do we name our substituent according to the IUPAC nomenclature rules? What are we going to call it? Okay, 2-propyl, I think I heard out there. All right, so this is 2-propyl 1-heptanol. That's the name of this particular compound. Okay, any questions? All right, let's do another example. Okay, what's our longest chain containing the carbon bearing the oxygen? 6 carbons in this case. Some people say 4. It doesn't have to start at the oxygen. It's just the longest chain that contains the carbon bearing the oxygen. So in this case, it would be 6. So what's our parent name going to be? Hexanol. Okay. What number are we going to put in front of hexanol? We're going to put a 3 in front of our hexanol. Okay. Notice if we were doing the first point of difference rule, we'd start at the right end because our first substituent will be on carbon 1. But we don't do that. The OH group has priority, so we have to number from the side that gives the OH group the lower number. So what goes in front of 3-hexanol in this name? 6-chloro. Yep, so this is 6-chloro, 3-hexanol. Okay. There is a common naming system that is acceptable for alcohols when the alkyl group that is attached to the OH is one of our simple alkyl groups that we have a common name for. And in that case, we would just name the alkyl group and just write the word alcohol afterwards. So this is a very common alcohol. What would we call this? This would be isopropyl alcohol. Okay. So there are 2 acceptable names for this compound. Isopropyl alcohol is one. 2-propanol is the other. 2-propanol is what you would call it using IUPAC nomenclature. Many people like to mix the 2 and call it isopropanol. Okay, technically, that's not correct. Of course, people will still know what you're talking about, but technically the correct names are either 2-propanol or isopropyl alcohol. Okay. So if we're naming cyclic alcohols, as you might imagine, since the OH group has priority, we're going to set the carbon bearing the oxygen as carbon number 1. And then from that carbon, we're going to number in the direction that gets us to the next substituent first. Okay. And if there's only one OH group, we don't have to use a number because it's understood that it will be at carbon 1. So let's look at an example. Okay, what's our parent name going to be? Cyclohexanol. Good. All right, we don't need a number in front of the cyclohexanol to indicate the position of the OH group, but we do have to put our substituents in front. So what's going to go in front of cyclohexanol? Okay, I heard a 2. What else? 2,5,5. Trimethyl cyclohexanol. Okay, 2,5,5 trimethyl cyclohexanol. Okay, so this is carbon 1 bearing the OH, and then we go counterclockwise in this case because we hit our first substituent next. Question? That's a great question. That's our next example. So you read my mind. We would use di or tri or tetra the same way we would with alkyl groups, the same way we use trimethyl here. So just right in front of the all is where you would put the di or the tetra or tri or whatever prefix you were using. So let's do an example of one of those. Okay. Now in this case, we don't drop the E because it would cyclopentanediol doesn't sound as good as cyclopentanediol. So whenever you have the di or the tri prefixes, then you leave the E in. Okay, so we'll call this cyclopentanediol. Because we have more than one OH group, we now have to use numbers. So what numbers go in front here? 1, 2. And then do we need something else? We need the prefix trans in this case. Okay, trans 1, 2 cyclopentane diol. Any questions about alcohol nomenclature? Okay, let's move on to ethers. So with ethers, we have two nomenclature systems. One that we use for simple ethers when the alkyl groups are small and simple and have their own names, and one we use when we have more complex alkyl groups. So we'll start with the simple ones. They're going to follow the pattern of alkyl, alkyl, ether, where we're going to name our two alkyl groups. We will put them in order according to the IUPAC alphabet, and then we just put the word ether at the end. So here's one. We encountered this molecule back in chapter 3. What is the name of this molecule according to this nomenclature system? Okay, so I heard methyl tert-butyl ether. There's a story behind that. Is that the correct IUPAC name? It's actually tert-butyl methyl ether, because in the IUPAC alphabet, the tert prefix does not count. In the IUPAC alphabet, tert-butyl starts with B, so we would call this compound tert-butyl methyl ether. But interestingly enough, the abbreviation for this compound is MTBE, because whoever gave it that abbreviation thought that methyl came before tert-butyl in the IUPAC nomenclature. And so when you see the abbreviation MTBE, it's referring to this compound, even though it's actually called tert-butyl methyl ether. It should be TBME, but again, not everybody understands the finer points of IUPAC nomenclature. And then if we have a symmetrical ether with the two identical alkyl groups, of course, we just use the prefix di. So our BAT molecule is diethyl ether. And this is probably the most common ether. It's used widely as a solvent in the lab for a variety of purposes. It used to be used as an anesthetic, but not anymore. So if you hear somebody just say ether and they're referring to a specific compound as opposed to a general class of compounds, they would be referring to diethyl ether. Okay. So what do we do if we have a more complicated alkyl group that is not one of our simple ones that we have a name for? So we're only going to focus on ethers where one is simple and one is complicated. We're not going to name any where both of them are complicated. What we do in that case is we name the simpler ether, the simpler alkyl group plus the oxygen as a substituent, and we name the more complicated alkyl group as an alkane. And so we're going to use the term alkoxy to refer to an oxygen and an alkyl group attached to that oxygen as a substituent. So the type of alkyl group it is going to replace the alk. So we could have a methoxy group or an ethoxy group or a propoxy group and so forth. And we'll just name that as a substituent of an alkane. Unlike alcohols, these alkoxy groups have no special priority. So we will treat them the same as alkyl groups. We'll treat them the same as halides. We'll use the first point of difference rule when numbering, and there's no special suffix on these compounds. So let's name one in this fashion. Okay. So what's our longest chain? Okay, so what's our parent name going to be? Okay, this will be a hexane. Which end are we going to number from, left or right? Left. We're using first point of difference rule. We don't care that the oxygen is closer to the right. We're just going from the left because we hit our first substituent. And what are we going to call this group as a substituent? Okay, that's a methoxy group. Okay. So what's going to go first in our name? Okay, so 4-methoxy goes first. Okay, what goes next? 2-methyl. I didn't leave myself enough room, so I'll have to erase that. 2-methyl hexane. Okay. So in this case, there's no curveballs with the IUPAC alphabet. Methoxy does indeed come before methyl. So that's how we name this. Any questions on our naming of ethers when one of the groups is more complex? So there are 2 common cyclic ethers that you will see that have common names associated with them. This one is referred to as tetrahydrofuran. Tetrahydrofuran is one of our polar aprotic solvents. It's abbreviated as THF. And this is a derivative of a common nomenclature system. You don't need to worry about where that came from. But this 5-membered ring is referred to as tetrahydrofuran, 5-membered cyclic ether. Less common, but common enough to have its own common name, is the 6-membered cyclic ether, which is tetrahydropyran, or THP. Okay, so those are 2 common cyclic ethers that you'll want to know the structures of. Questions? Okay, so you will be excited and thrilled to learn that there are actually 3 nomenclature systems for naming epoxides. Only 2 of them are common. One of them is only used in rare circumstances. So we'll go over the 2 that are the most common, and then we'll just briefly show you the 3rd one. So one way to name an epoxide is to just name the chain of carbons that the oxygen is attached to, and name that as an alkane, and name the oxygen as a substituent of that, referred to as an epoxy group. So we could call it, an epoxy alkane. And then we would just put numbers in front of epoxy indicating which carbons of the chain the oxygen is attached to. So here is a sample epoxide. How many carbons in our carbon chain? 4 carbons. So we're going to call this epoxy butane. And which carbons of epoxy butane is the oxygen bonded to? In this case, it's 2 and 3. So this is 2,3 epoxy butane. And then do we need another prefix in front of that? What do we need? We need cis. Okay. So this is cis 2,3 epoxy butane. You can also have an epoxide attached to a ring, to another ring, that is, to a cycloalkane. Okay. So we would call this epoxy cyclohexane. And to me, it doesn't seem that you would need numbers in this case, but I've always seen numbers used. So I guess somebody at IUPAC has decreed that you would call this 1,2 epoxy cyclohexane. Any questions? All right, so our second way of naming epoxides treats the epoxide ring as the parent and names the substituents that come off of the epoxide ring. And the IUPAC name for epoxide is oxirane. Okay. So when you see the word oxirane, that means three-membered ring with one oxygen present in the ring. And the oxygen is always going to be atom number 1 because oxygen has a higher atomic number than carbon. So if we were going to name this compound as an oxirane, what would go in front of the word oxirane? What substituents do we have coming off of our three-membered ring? Okay, methyl groups, how many? Okay, so we would put dimethyl. What carbons are they on? What numbers go in front of dimethyl? 2, 3. Remember, the oxygen is always atom number 1. So in this case, it's 2,3 dimethyl. And then do we need another prefix in front of that? We need our cis in this case as well. Okay, so this is cis 2,3 dimethyl oxirane. So either name is correct for this particular compound. You can just pick the one that you would like to use, but I can pick the one I want to use, and so if I write either of these names, you would have to be able to convert that into this structure. Question?
Which of these is the IUPAC?
They're both acceptable under IUPAC nomenclature. I'm guessing that IUPAC invented this one, and this probably existed before IUPAC, but they've decreed that we can still use it. That's just my guess. But okay, any more questions, or are you ready for the third way of naming epoxides? So our third method of naming epoxides is typically only used for very simple epoxides, and it is derived from the fact that in the chemical industry, epoxides are usually synthesized from alkenes. Epoxides are very useful in the chemical industry. In the very last chapter of the year, chapter 31, at the end of 352M, we'll learn about how epoxides are building blocks for polymers. And so you can make interesting polymers using epoxide starting materials. And those epoxide starting materials come from alkenes. And so this third system refers to an epoxide as an alkene oxide. So what you do is you just name the alkene that was the precursor to the epoxide, and you put the word oxide on the end. And I've only seen this used for very small, very simple epoxides that are used in the chemical industry. And one of the most common ones is oxirane itself. You would just call this oxirane if you were using IUPAC nomenclature. But if you were making this epoxide from an alkene precursor, if you were attaching the oxygen to an alkene, what alkene would have been the precursor? Our very simplest alkene. What's it called? Yes, it's called ethylene. So this would be ethylene oxide. Okay, so this particular epoxide is usually called ethylene oxide instead of oxirane because it's commonly used in the chemical industry and it's commonly made from ethylene. But other epoxides, not so much. Okay, there's propylene oxide, but I've never really heard this term used beyond those two epoxides. So that's one that you probably won't see in the class, but you might read it somewhere else. Question?
So this is, you can't really use this when you have branches and stuff.
No. So this is only for the simple ones. All right, let's talk about physical properties. With two alcohol molecules, what are the strongest types of non-covalent attractive forces that you could have? Okay, you could have hydrogen bonds between those two alcohols, the OH groups, the hydrogen of one, the oxygen of another. What about ethers? Can ethers engage in hydrogen bonding to each other? No, they cannot. So what's our strongest type of intermolecular force? Okay, we have dipole-dipole forces with ethers. Can ethers engage in hydrogen bonding with water molecules? Yes, they can. Okay, so what that tells us is that if we're comparing boiling points, an alcohol should have a higher boiling point than an ether of the same size, which in turn would have a higher boiling point than an alkane of the same size. And it also tells us that both alcohols and ethers would be soluble in water as long as you had 5 carbons or less for each oxygen that you had in the molecule. Okay? So we have a table here that summarizes this, the fact that we've just gone over. So here we have an alkane, an ether, and an alcohol, all of essentially the same size. And you see the boiling point increases as we go from left to right. Here you see that if we're comparing different alcohols, the alcohol with the greatest surface area has the highest boiling point. So if you have the same number of carbons, primary alcohols would have higher boiling points than secondary, which in turn would have higher boiling points than tertiary. The book is telling you here that you have more hydrogen bonding, stronger hydrogen bonding if your alcohol is less hindered. That is true, but you could also just look at it the same way we did in chapter 3 and recognize that you have more surface area with your primary alcohol. So you have more van der Waals forces, and the magnitude of those van der Waals forces decreases as your surface area is decreasing. Okay? Any questions about physical properties of alcohols? So there's a whole host of interesting alcohols, both in nature and compounds that have been synthesized. Here's some naturally occurring alcohols that we already talked about in chapter 5. We mentioned cellulose and amylose. These are carbohydrates, and carbohydrates are polyols, tons and tons and tons of alcohols present in carbohydrates. And we learned that a small difference in stereochemistry between cellulose and amylose causes a big difference in their structure as well as their function. Okay? So on most college campuses, ethanol is the most popular alcohol. And in fact, most universities will have a course dedicated to the chemistry of alcohol in the brewing process. It's big business. Brewing is a major industry, and so in the production of alcoholic beverages, a major industry, and so it's actually an important class that is taught at many universities. Of course, we don't have a class like that here, but solely for the purpose of allowing you to seem informed, to be informed when you have conversations with friends from other universities. We're just going to spend a few minutes and talk about ethanol and alcoholic beverages. But this is not for personal use. This is just for you to understand the process and be able to converse with others from other institutions. So the way that alcoholic beverages are produced is that you take some material, some plant-derived material, which has carbohydrates in it, like all plant-derived material does. You incubate it with yeast, which is a microorganism, and the enzymes that are present in the yeast are going to break down the carbohydrates and convert those carbohydrates, or at least some of those carbohydrates, into ethanol and CO2. So you'll see bubbles that are given off slowly in the process as that carbohydrate material is converted into ethanol and CO2. So if we start with barley and we incubate barley with yeast what do we get? Right, but what is the beverage called? The beverage is called beer. And do not worry, I'm not going to tell anyone's ecclesiastical leaders that you know these answers, okay? That's a fairly common one. That most people recognize that beer comes from barley, okay? What about grapes? What beverage do you get when you incubate grapes with yeast? We get wine, okay? Again, and none of your voices can be identified on this video, so don't worry that we're filming this. I'm the only one that would have any feedback, I guess. What about potatoes? You get vodka by incubating yeast or potatoes with yeast, okay? So there's a limitation to the alcoholic beverages that can be created with this process because the enzymes in the yeast are only able to make a solution that's about 15% ethanol. And the rest, of course, is water. So the way I look at it is the enzymes become inebriated at that point. There's too much ethanol in the solution, and they no longer work, okay? But there are alcoholic beverages that have a higher alcohol content than 15%. How do we get those? Yes? There's a way to concentrate the ethanol, and I think I heard the answer out there. Distillation process, yeah. So if you do a distillation, then you can distill off the ethanol, and it's mixed with the water. It's hard to get 100% ethanol, but not impossible. But so if you distill some of these beverages, you can make other beverages that have a higher alcohol content. So if you take beer and you distill beer, what do you get? Whiskey. I will not tell anyone that you knew that answer, okay? So you get whiskey from distilling beer, okay? And this process was discovered in Scotland. They're very proud of the fact that they discovered distillation, but it's practiced all over the world. It's big business. George Washington was a whiskey distiller. He sold a lot of whiskey. That was one of the ways he made money. Okay. What do we get if we distill wine? What was that? Liquor is just kind of a general term for any of these. Anything that's distilled is usually referred to as a liquor. So that is correct, but there's a more specific term we could use. I'd be a little worried if people knew this one because it's less common. Brandy. Oh, okay. Or cognac. My expertise in this area is quite limited, and so I don't know the difference between brandy and cognac. I'm not sure what makes one and one the other, but distillation of wine can give you these two beverages. What do you get when you distill vodka? Stronger vodka. Good answer. Yes. Yes, and I think in most countries such as Russia where they drink vodka, I don't think they mess with the weak stuff. I think they just go straight to the distilled spirits at that point. Okay. So that's all we're going to talk about on this subject. Like I said, just a very brief introduction, just for your own information and not for your personal use. But there is something else that ethanol is used for. What does ethanol get used for other than beverages? What's that? Okay, it can be used in sanitizers and cleansing, and that use has gone up a lot in the last 7 months or so. A third thing, gasoline. It is used as an additive for oxygenating gasoline. So in Utah, probably, if not already, within a week or two, we'll switch over to gasoline that has about 10% ethanol in it because it burns cleaner. And in the wintertime in Utah, we have problems with air quality due to inversions. And so to mitigate that, we try to burn cleaner fuels. And so oxygenated fuels, fuels that have oxygen in them as opposed to just fully hydrocarbon fuels, are cleaner burning. they put less particulate into the air. So in addition to those fuels that would be about 10% ethanol, there is a fuel known as E85, which is 85% ethanol and 15% gasoline. This is the highest percentage of ethanol that most engines can burn, and it has to be a special engine to do this, but most cars these days are equipped to take E85 as a fuel. Okay, so that's very oxygenated. There are some problems with it, though. Even though it's cleaner, it's actually less efficient. You get 30% less gas mileage, miles per gallon, if you use E85. So it's going to cost you more. Unless the E85 is cheaper than gasoline, it's going to cost you more to fill up your tank. So if gasoline cost $3.20 per gallon, I know it's less than that now, your E85 would have to cost about $2.80 per gallon in order for it to cost you the same amount of money to fill up your to use that gas. Question.
Does it hurt like older engines? Or is it the battery?
So it is. It can be corrosive. It's more corrosive to the engine, and so yeah, that's why you have to have a newer engine. You might have to change your oil more frequently. Another problem with E85 is we have no infrastructure, no pipeline infrastructure for transporting it around the country. So you have to put it in trucks to take it to the gas stations. And what do those trucks run on? Fossil fuels. They run on gasoline. Okay, so that doesn't make a whole lot of sense. But there is a movement to use E85. There are benefits to it. What are the reasons why we would want to use this? Yes? Renewable. Very good. So what you're referring to is that gasoline is a fossil fuel. It comes from the earth. The carbon that's locked up, the carbon in the fossil fuels has been locked up in the earth for tens of thousands of years. And then when we burn it and convert it into CO2, we're increasing the CO2 in the atmosphere. But the carbon in ethanol is coming from plants, and the plants pulled that carbon out of the atmosphere. So we're just returning something to the atmosphere that was already there, basically just contributing to a cycle. So the fossil fuels are going to have an increased greenhouse effect, increasing climate change, global warming, whatever you want to call it, whereas the renewable fuels would not be doing that. Okay, and then another factor is that fossil fuels are limited. There are no more dinosaurs, last time I checked, dying and creating fossil fuels. So we have a finite supply of fossil fuels. But we can keep planting plants and harvesting plants as long as we don't over-harvest them. And so we have an ability to continually get the sustainable ethanol fuels. So there is a movement to use more E85. There are some problems. Where does ethanol come from in the US? Corn. And the problem with getting ethanol from corn is that we eat corn, and a lot of farm animals eat corn. So if you're buying pork, certainly that pig was fed with corn. And so if we're taking something that could feed us and burning it up in an engine, and people are starving in America, then that doesn't make a whole lot of sense. So a possible solution to this is to get the ethanol from the corn stalks, the part of the plant or other plants, not just corn, that we don't eat. The problem with that is the carbohydrates that we're converting to ethanol from the corn that we eat is coming from amylose or starch. The carbohydrates in the part of the plant that we don't eat is coming from cellulose. And just like our stomachs can't break down cellulose, it's harder in an ethanol plant to get ethanol from cellulose than it is from amylose. So it's more expensive. This is called cellulosic ethanol. And there are some plants in Iowa and maybe other areas of the Midwest that do generate ethanol from the stalks, the parts of the plant that we don't eat. But it's more expensive, and so it's not very common. Economics really drives everything, right? People want to save the environment, but if it's going to cost you too much money to save the environment, nobody's going to do it, right? Because you have to be able to make a profit if you're in business. Another solution, sugar cane. Another problem that you have is it's an energy-intensive process to get the ethanol from the corn and the corn stalks. And where's that energy coming to fuel these plants? Fossil fuels. So again, that's not very efficient unless you're using renewable energy. If you have these plants near a source of renewable energy, then that would be reasonable. Sugarcane. In Brazil, they have tons and tons of sugarcane, and it's actually more efficient to get the ethanol from the sugarcane. They actually burn the stalks in the plants to provide the energy for producing the ethanol. So they're not burning fossil fuels. It works pretty well, but we don't have a lot of sugarcane in the US. That wouldn't work for us very well. Okay. Another idea that was put forth by a chemist named George Olah, who won the Nobel Prize many, many years ago, is what he refers to as a methanol economy, or he calls it the human carbon cycle. This is from a paper he published about 9 years ago. So his idea is to take CO2 out of the atmosphere. There's plenty of CO2 in the atmosphere. What if we can capture that CO2? We can react that CO2 with hydrogen, and we can convert that into methanol. Right? Methanol is close enough to ethanol that it can be used just as easily as a fuel. And you would also, in this process, make some dimethyl ether, which also could be used as a fuel. Both of these would be viable. You could burn them in combustion engines and use them as a fuel. Now, you need a catalyst for this process. You need a metal catalyst, but we have catalysts that work for this reaction, so that's not a problem. There are some problems, though. One problem is the storage of the CO2. We have technologies for capturing it from the atmosphere. And you could put these devices close to plants that are emitting a lot, not plants that grow, but like a manufacturing plant that emits CO2. And you could just capture that as it's going instead of having it go into the atmosphere. But I'm told the hard part is getting the CO2 out of where you've got it stored into where you can get it to react with the hydrogen. That's actually more challenging. Another challenge is the hydrogen. Where does the hydrogen come from? The answer would be natural gas or fossil fuels. Most hydrogen that's used today comes from methane. So you're defeating the purpose using a fossil fuel to create a renewable fuel. You can get it from electrolysis of water, but you need two things to do that. You need a lot of water, right? In droughts in Utah, certainly we don't have a lot of water to convert into hydrogen. And you need renewable electricity. Again, if you're burning natural gas to create a renewable fuel, that's not really renewable, is it? So there are some problems with this cycle, but it does work in some places. Iceland is the one place in the world where this is actually practiced, and it makes good economic sense and good environmental sense, because in Iceland, they have a lot of geothermal energy. Electricity is basically free in Iceland because of all the geothermal energy they have. They have plenty of water that they can electrolyze with this renewable energy to generate their hydrogen. And then they pull CO2 out of the atmosphere, react it with a catalyst in a plant, and out comes their methanol and their dimethyl ether that they can use as a renewable fuel. So it works in Iceland. It doesn't really work in other places very well yet, but this is a serious problem that we need to solve, the renewable energy problem, because fossil fuels, as we've discussed, have their limitations. And so we do need to find replacements for them. And so hopefully some of you in this room will work on this problem in the future because there are still many, many aspects of it that need to be ironed out so that we can replace our fossil fuels. All right, so that's it for today with our discussion of interesting alcohols. We'll talk about ethers and epoxides on Monday. If you have not taken the exam yet, you should get to the testing center quite soon. Good luck and have